Okay, so here we have this open box, right? And actually, that's what we want to create is the open box. And we have this sheet of paper. And it's 16 by 30, so they've kind of given you a lot here. But what's going to happen is when you cut out these little pieces here, if this is 16, you're cutting out size X here and here, which is why they have 16 minus 2X. So that's one of the dimensions. Then here you have the 30, but then you're cutting out whatever size X here and X here. So that's where we get 30 minus 2X. How do you find the volume of a rectangle or a box or whatever? What's the volume formula? Yeah, it's length times width times height. So we have the length, we have the width. What's the height? It's X, so it's right here. Okay? So what we have is the volume being equal to the length, which is 30 minus 2X times 16 minus 2X times X. Okay, if we are looking to maximize the volume, we're going to have to take the derivative, right? We've already figured that out in the last two problems. So what would you say we should do with this first? Yeah, I would totally multiply it out, right? Mm-hmm. Yes, absolutely. So I would FOIL this first, then distribute. I mean, it doesn't really matter. So we have V is equal to, so what is that, 480? This is negative 60, negative 32, so what is that, negative 92x? And then this is plus 4x squared. Okay, I'm just multiplying. And then we need to distribute that x, which is our height. So our volume formula, and I'm going to rewrite this in standard form, okay, is 4x cubed, okay, that's this first one, minus 92x squared plus 480x. Is that right? Did I miss something?
Was it 4x squared? Right, because you distributed, yeah.
Yeah. Am I good?
Yeah.
Okay. So, because we want to maximize the volume, we already determined that we have to take the derivative. So this, what's the notation here? Careful. Yep, dv dx. The derivative of the volume with respect to x is 12x squared. Oh, is that 184? Yeah. 184x plus 480. Okay, we're going to have to factor this, but I need to, can I take out a greatest common factor?
I hope so.
What do you think I can take out?
12 times 14 is 184.
12 times 14?
4 maybe?
That might be higher.
Definitely a 2.
Definitely a 2, yes. Yeah. Yeah.
Yeah, never mind.
You can have a calculator. Can I take out a 4?
Definitely
480, yes. 12, I can take out a 4. What about 184 divided by 4? 4 would be 16, 24. Yes. Okay. Let's take out a 4. Wow. 3x squared. When I take out 4, so this is 4, 16, 24. What is that? 46?
Yeah.
X plus. Is that 120?
Mm-hmm.
Okay. I need two factors of 360. Oh, come on. Two factors of 360 that add up to negative 46. 360. What are the two easiest factors of 360?
6 and 60.
36 and 10.
You said the easiest. Oh. This is I'm kidding, sorry.
Okay. What did I say? X minus 36. X minus 10. Divide by 3. Divide by 3. Okay. So this is 4 times x minus 12. And 3x minus 10. Oh my goodness. Okay, this is my derivative. Finally. Okay, it takes work. You have to do it. So then basically I have my critical numbers, right? We have critical numbers where x is equal to 12 and 10/3, which is 3.3 repeating. Is that true? Okay. So here's the deal. What we're saying is there is a possibility that I would cut out a square of 12 by 12. Let's look up here. If this is 16 and I cut out 12 from one side, am I going to have enough to cut out 12 from the other side? Okay, this is how you're going to find your domain restriction. You will always take half of your smaller side. And the reason why is because if I were to cut 8 this way and 8 this way, I lose a side, right? So what we're saying is our dimensions have to fall between 0 and 8. Okay, they can't be equal to them. Okay, does everyone understand why we don't pick the larger side? That question always comes up. If I were to say, if I pick the dimensions of the larger side, this is half of this is 15, right? So I'm saying that the side of my square could be, at max, 15 by 15. But if I want to cut a box out of each side of this side of my paper, if I cut out a 15 inch by 15 inch, how much is left if I try to cut from the other side? This is 16 total. If I cut out 15 by 15, what's left? 1 inch. I don't have enough to cut the square from the other side. It's not going to be a rectangular box. Do you see? But I could cut out 8 and 8 from here, but we're saying let's say it's 7.5. I still have enough. Does everyone understand what I'm saying? Okay, so you always want to choose the smaller side, and you take half. Okay, because you're cutting from each side. It's something to think about. So if my domain restriction is from 0 to 8, can I eliminate one of these critical numbers?
Yeah.
Yes, this one. Okay, we already said that we can't use it. 3.3333333 falls in here. True? Okay, so we still need to test it. Okay, and remember in the directions, in the strategies, it said if you have a physical limitation, that's a physical limitation. That's what they're talking about. So you have to identify a domain restriction, at least for yourself. Okay, so let's take the derivative and test. So what is this? dv dx. And we want to test, what, 10/3, which is about 3.3 repeating. Pick a value to plug in on the left. Actually, whoa, what? 0? Okay, so 0, negative. 0. So this is positive, right? So this is increasing, positive. I don't know, can we pick 4? Okay, so 4 minus 12, negative. 3 times 4 is 12, minus 10 is positive, so this is negative. Okay, we wanted to maximize, true? Largest volume. So is this going to work? Yes. Okay, so because this is a square, they are asking us for the dimensions of the square that we're cutting out from each corner. What are the dimensions? Well, don't just what did you solve for?
X.
Right, so you said 3, but is it really 3?
No, it's number 3. Oh, wait, no.
It's 3.333, so why don't we just use the fraction that we had? I know we don't typically say, oh, I'm going to cut out 10/3 inches. Like, that's just not something we say, but that was the calculation. So we have 10/3 inches by 10/3 inches. These are the dimensions, okay? How did we find that? What's my justification? That's right. By the first derivative test. Okay, by the first derivative test. Our volume has a relative max at 10/3 because dv dx changes from positive to negative. Is that true? Questions? You can figure out how to maximize, so it's probably the smaller one. Okay, here we go. I'm just going to move over. Here we have a cylindrical can, okay, that is closed at the top. And that's kind of important because when we're talking about materials, if it was open at the top, think about like a soup can. I don't have any cans in here. If it was closed at the top, we have to consider the material that would close it at the top. If it's open at the top, we don't consider that. Does everybody understand what I'm saying? So you have to make sure you read the problem very carefully. So our cylindrical can is closed at the top, and it holds 800 cubic centimeters of water. What does this represent, 800 cubic centimeters? Yes, this is volume. Okay? We want to find the height and the radius that minimizes the amount of material. Okay, so we are environmentally conscious here to manufacture this can. Okay, so if I want to know, okay, there's no soup or anything in this can. So is the can technically hollow? Okay, so if I want to figure out, I want to minimize the amount of material, what am I calculating? The surface area, that's right. Okay, so we're looking for the surface area of basically a cylinder. Okay, so this is what I want you to think about. I'm going to show you right here. Okay, remember, I'm not an artist. So here's my can. Oh, it's going to be bad. Okay, like this. And it's closed at the top, right? And obviously closed at the bottom if you have a can. Oh, boy. Okay, so my you're looking at this from an angle. That's why it's like kind of slanted. Just saying. I don't know. How would I figure out the surface area of the top? What am I looking for? The area of a circle. How many circles do I have? Okay, so we have 2 pi r squared. Okay, because there's 2 of them, right? Top and bottom. What happens if I were to slice this can? I don't have the top and the bottom. I took them away. And I open up this can. Think about like it's a rectangle. It is. So what we have are 2 circles plus a rectangle. Does that make sense? So then this would be plus, what's the rectangle? It's what?
Times circumference.
Yes, it's a circumference because it's going to be circular, right? So I have, what is this? 2 pi r. That's the circumference, right? But don't I have to consider this too? If the circumference is like this, it's just like this, but I need the height of that can. So this is plus 2 pi r h. Okay, this is the surface area of this can. So it's kind of a lot to think about because this right here is the circumference, this is the height. Okay, I have a question. What is wrong with the right side, or I want to say wrong, but what is the issue that I would have with the right side of my...
Variables.
Yeah, yes. There are 2 variables. Okay. Here, they said that the volume is 800 cubic centimeters. How do you find the volume? You guys told me already. Yeah, pi r squared h. Right? So we know the volume. This is 800 is equal to pi r squared h. What do I want to get rid of over here? I have 2 r's right here. Like, not 2, but there's 1 here and 1 here. So if I get rid of this h, I could solve for h here. Agree? So now we have h is equal to, 800 over pi r squared. So now I can make a substitution. We have not even taken the derivative yet. So our surface area, or basically our area, is equal to 2 pi r squared plus 2 pi r times what we found for h. So this is 800 over pi r squared. Can we simplify just a little bit before we take the derivative? It's a lot of stuff. This. Yes? So let's see, area is equal to 2 pi r squared. This is still plus 1600. My pi's go. So this is 1600 over r. Can I write this as 1600 r to the negative first? Just so I can take the derivative? Yes? Does everyone understand where that came from? Okay. Are we ready to take the derivative finally? Man. So how do I want to label this?
dA over dr.
Yep. Is equal to, careful, is this a variable?
No.
No. So I'm focusing on the r squared. What's the derivative of r squared?
4
Yeah. You're right. This is 4, because it's going to be dr, so that'll go away. 4 pi r plus or minus 1600, and this is going to be r to the negative second. So can I throw that on the bottom?
Yeah.
Okay, do you remember that problem that we just did on the very first page where we had to get a common denominator?
Mm-hmm.
This is the same scenario. So what's my common denominator? It is r squared. So that means I need to multiply this by r squared. So this is 4 pi r cubed minus 1600 over r squared. Okay, so here's my question. If this is the derivative, and we are obtaining our critical numbers from the derivative, which is from the numerator and the denominator, remember we're looking for the radius so that we can figure out the surface area. When I set the denominator equal to 0, we're solving for our radius. What does r equal? So what happens when you have a radius of 0? You got no surface area. So can I even use that as a critical number? Does everyone understand why? Okay, it needs to make sense. Okay, so now I need to solve for r in the top. So this is where we're definitely going to need a calculator. So we've got 4 pi r cubed is equal to 1600, because I set it equal to 0 and added 1600. We're going to divide by 4 pi, so r cubed is equal to 1600 divided by 4 pi, and then what? Take the cubed root. So r is equal to the cubed root of, this is what, 400, excuse me, over pi. Calculators, do me a favor. Take the cube root of the quotient of 400 over pi. The cube root of 400 over pi? It depends on how you put it in your calculator. Hang on. Yeah, that's what I got. You have to be careful how you put it in your calculator. I got 5.031. Okay, so if you have 400 over pi. Ooh. Because I only took the second root. Haha. Square root. I got it. I got it. I was like, none of us are right. 1 divided by 3. Okay, there we go. All right, so this is approximately 5.031, and what's my unit of measurement here? Centimeters? Okay, now I still need to test to make sure this is a what? I do, so we're going to go down here real quick, and we're going to use the cubed root of 400 over pi. Okay, remember we can't use 0, but that is my left-hand marker. If this is 5.031, pick a number that you want to put in here. Okay, pick 1. If you plug in 1, you're looking to see positive or negative. Well, already 4 pi times 1 cubed minus 1600, what's it going to be? It's definitely negative. Okay, I don't know, pick whatever you want. 10? Ooh, my gosh. That's 4 pi times 1,000. So already you can see what's going to happen. So it's definitely positive. So this is definitely a relative min. Agree? Okay. So we will have to make our justification statement, but it says that I need the height and the radius. I have the radius. How do I find the height? Can I plug it in right here?
Yep.
Because I just happened to move my paper up. So this is 800 divided by pi r squared, and use 5.031 just to save yourself some time. So this is approximately. Anybody? TikTok. Let's see. Who? I didn't hear what you said. I seriously did not hear what you said.
I did wrong.
Oh, okay. Is this right? Is this the right setup? That's what I got. I just need someone to confirm for me something, anything. Okay. Okay, so 10.061. Let's talk really quick about rounding, just one more time, because it was an issue on this past test. It doesn't really say in here, so you could round it to 3 decimal places or truncate at 4. I've been rounding to 3, so 10.061 centimeters. Truncate means at the 4th one you just chop it off. So what would my justification be? What test did we use? Yeah, so we would say by the first derivative test. What are we looking for? To minimize. Yes. By the first derivative test, the surface area has a relative min at, and you can write your crazy radical here, the cube root of 400 over pi, because I'm sorry, not everybody at once. I can't hear you when you're all talking. Because why? What goes from negative? What changes? dAdr changes from negative to positive. Yes, you need to make sure that you're telling us that you use the derivative.